Greetings. In last lecture, we learned about the prerequisite required for the structural analysis. Today, we will be discussing on principle of superposition, which we say is the basic for structure, basic principle which is used for in structural analysis of determinate structure. For that, let's go towards the statement of this principle of superposition. The statement states that the total displacement or internal loading, that is stresses at any point in a structure subjected to several external loading, can be determined by adding together the displacement or internal loading, that is stresses caused by each of the external loads acting separately. Means what here, if a member is subjected to several external loads, it becomes a complex job for estimating the displacement. Then in that case we can have simplification, that we can separate individual cases and then we can analyze individual case, and after analysis of this individual case we can have a summative effect to find out the total displacement of that section. Let us elaborate this with a reference to an example. Let us say here the example beam is like this, which is subjected to combination of loads where the UDL is spread over a span of A is spanning over the length of the beam L, and the beam is subjected to point moment also at one end. So here these two forces are responsible to create a deflection. If I want to know the displacement of this total structure, it will become a complex job to find out the resultant displacement. Then what I can simplify this into a simplified cases like beam subjected to partial loading over the span, that is W effect of UDL only. In the second case, what I will do, I will consider the effect of point load at one end, and I will try to find out the displacement for these individual cases. Let us say X is the total displacement of the beam under the several external loads, whereas V1X is the displacement of the beam under the loading UDL only, and V2X is the displacement of the beam under the point moment load. Then at the last, what we can have, the deflection equation of complex beam can be rewritten as a Vx is equals to V1x plus V2x. This principle help us to resolve the complex geometry and get the result of it. But this statement is valid for some cases only. The validation is that this is valid for material which have linear static behavior or which obeys the Hooke's law. And the second one, the geometry of the structure undergoes the significant changes, but the displacements are too small, or we are going to apply we are going to neglect it, or we can say we are going to apply here small displacement theories. Then only this equation is valid. Let us go towards a numerical example on this one. For that, I have considered a case here. The beam, simply supported beam, is subjected to partial UDL or running over the length of the beam, and a point load at one end which is of magnitude 4 kilonewton per meter, and UDL is 6 kilonewton per meter spread over a span 6 meter, whereas the overall span of the beam is 10 meter. So I want to analyze this one, that this is a complex loading, but then I can't have a standard solution for this. I have to go for iteration method. So what I can do here, I can simplify this into a simpler cases. Like, for simplification, what I will do, I will split this beam into two simple cases. The very first case is that the beam is one with a distributed load, and like this I will consider the UDLs acting separately, and the second case, beam 2 with a point moment load acting on the section like this. So here I have got two separate cases. Now I will try to analyze these two separate cases and get the displacement of these two separate cases. For that, I will apply the deflection for a beam 1 with a distributed load over the part of the beam is given by. We are having this standard solution for the standard case where the partial UDL is going to act over the entire span of the beam. So we have a relation minus W x divided by 24 L EI. A raised in bracket A raised to 4. A is nothing but the span of where the UDL has been spread up, and 4 minus 4 A cube L. L is the total span of the beam, plus 4a square L square plus 2a square x square minus 4a L x square plus L x cube. Now for the I will apply the deflection equation for the second case, where we have a standard case here. Moment is being applied at one end, and the effect of this moment will be taken care for the calculation of displacement. It is given as V2x is equals to minus m L square divided by 16 EI. When we add let us suppose we are interested to have a deflection at a span 5 meter, that is the mid span of this one at a distance 5, Then what I will do, I will substitute the variables here. The variables are nothing but the intensity, magnitude of the load here. The UDL is of 6 kilonewton. I will put here 6, and the span which we have considered x is equals to 5. At x equals to 5 we want. Then here a is nothing but the span over which the UDL is distributed, that is 6. Likewise, I will substitute individual value in the equation, above equation, and the resultant value which we have, V1 is equals to minus 51.325 divided by EI. So we are going to consider this as a separate case, and then we are going to have a cumulative assessment of this one. For the second case, we'll apply standard equation minus m L square divided by 16 EI. After substituting the individual values of variables, we can get the resultant value as a minus 25 upon EI. And the last, what I will do, I will add this V1x and V2x to get the total displacement of this B. So Vx is equals to minus 76.325 divided by EI. This 16 will not come, it's by mistake. So you don't consider the 16 here, the resultant is minus 76.325 upon EI. Now let us go towards the concept of strain energy, as the syllabus is based on the concept of strain energy and extension for of this strain energy to analyze determinate and indeterminate structure. That's why we'll go towards the thorough insight of this concept. Okay, so let's start with the definition of what is an strain energy. So the definition can be stated as when an elastic member is deformed under the action of external force, external loading or force, we can say, the member is said to have possessed or stored energy, which is called as a strain energy of the member or resilience of the member. It's also called as a resilience of the member. So what the definition says, a elastic body is what elastic member is there. Okay, so elastic member undergoes deformation, and it undergoes means it has stored certain deformation under the action of external forces, and that deformation which is stored by that member is called as a strain energy. Okay, so or we can say it is a resistivity of the member against the applied load. That's why we can call it as a resilience of the member also. Now I will quote the second statement here. The strain energy stored by a member so deformed is equal to the amount of the work done by the external forces to produce the deformation. Means what he says is stored energy is directly is equals to the total amount of the work done by the external forces to produce that deformation. Okay, so remember this statement. We are going to use this statement in further analysis. Okay, let us have a estimation of strain energy for a particular material. For that, let us plot a response curve. This response curve has two parameters, force and displacement. For incremental force, we will have an incremental displacement here. Let us say I am interested to know what is the energy possessed by body at a particular level. Let us say this section is x1. At this section x1, I require the energy stored by the body. So that's why what I will do, I will find out the strain energy, which is nothing but the area enclosed under this curve at the section x1. Okay, so we can write this as a let's say U, capital U is the strain energy. We are going to denote the strain energy by capital U, which is equal to integration 0 x1 into P into dx. So 0 x1 it defines the limit for the area, and P into dx it defines the two coordinates here. P is the coordinate related to force, and dx is the incremental displacement, because x is the total displacement. I am going for a partial part. So that's why what I will do, I will go for incremental displacement only. So the relation will be integration 0 x1 P into dx. So if I write here strain energy capital U is equals to area under the curve. This energy stored is distributed over the entire volume of the member. That's why we can write strain energy density as small u as du divided by dv. It means a partial increment in the strain divided by partial increment in the volume. So let us quote this statement, and we'll recall this statement in further analysis. Now let's consider I have make a mathematical rearrangement in the equation like capital U divided by V, and on the secondary part integration 0 x1 P into dV divided by V. So what I have done here, I have divided both the side of equation by the volume, so that I can replace this parameter as a strain density index. So I can write strain density as equals to integration 0 to x1 P into dx divided by. Now what I have done here, I have replaced this volume with a product of area into length. Area is area of cross section area of the member multiplied by the length of the member. We can write it as volume, Again, if I want to separate this one, I can separate these two entity like P by A and dx by L, which will where we can sense that this one the P by A is nothing but the stress, and the dx by L is nothing but the strain, incremental strain here. So I can replace this equation like uh, the strain density is given as 0 to epsilon 1. Epsilon 1 is the strain at the displacement x1, sigma x into d epsilon x. This is nothing but incremental strain, and here subscript x defines the direction in which I am going to consider the action of the force. Okay, so after solving this equation with applying the relationships of Hooke's law and the basic relation for finding out the integration of them, integration, we can get the relation strain density is equals to sigma square divided by 2e. Now we'll recall back the statement which we have made. Strain density, strain energy density U is equals to du divided by dv. You see a small increment in the strain divided by increment in the volume. If you rearrange this one to get the total value of strain energy, I will rearrange this equation. This equation can be rearranged as U equals to integration U dv. Means I am going to extend the distribution of strain energy density over the entire volume. Okay, then after that what I will do, I will substitute the value of U, because just now we have find out the relation, that is strain energy density is given as sigma square by 2e. So we'll substitute this value sigma square divided by 2 into dv over the, so entire volume will be the estimate of strain energy possessed by that deformable member or deformable body. Okay, now we'll extend this concept with reference to the various action of the action which has been played by the applied forces on the member. So let us extend the concept of strain energy towards the axial loading, where we'll make a statement here: strain energy is stored due to the axial loading. So here there will be there we are going to consider the effect of axial load, and for that we are going to estimate what amount of strain energy is going to stored by that deformed body under the action of tensile force. So for that, let us consider a section as shown here, which is subjected to pull tension force P over the span DL. Span DL. So we can say that sigma is nothing but P by A, means total tension applied per unit area. Then we can after substituting this value in strain energy relationship, what we can get: U is equals to 0 to V P square divided by 2E A square into dV. Now what I will do, I will replace this volume with reference to the relation dV is equals to A dl. So A into dl is cross section area of the member multiplied by the length, elemental length. Then in that case we can write total strain energy possessed by this body will be equals to 0 to L P square divided by 2 EA square multiplied by A into dl. One power of A get cancelled here. What remains is U is equals to P square L upon 2 AE. This is the extension of the strain energy formula with reference to the axial loading. So likewise, we will do more exercise related to various loads like bending moment, shear force, and torsional stresses, and we will see this case in upcoming lectures. Till then, stay at home, be healthy, and be safe. Thank you.